Afternoon, everyone. Last time we talked about the efficiency of DC motor, how to calculate the loss. And simply we have two kinds of loss. One for the copper loss, that's I squared times R, armature resistance or field resistance or any other resistance if we have starting resistance that we're going to talk about today. And the constant loss, which is rotational loss. That's a mechanical loss due to friction, windage, and all the things. Today, we are going to talk about speed control of DC motor in general. So we'll start with the torque speed characteristic. To understand how to control the speed of DC motor, we have to know what is the relationship between the speed and the torque. In separately excited DC motor, we have the armature, and the voltage across the armature, we call it EA. That's supposed to be negative. And we have in series resistance that represent the resistance of the winding on the armature, call it RA. And we have the voltage, DC voltage supply, call it the V terminal. And the current, supposedly that the current we called it last time, the terminal current IT. And if we don't have any resistance or anything in parallel, it's the same, would be like IA, the armature current. Then the field, we said that we have winding, the field winding, and maybe we have like resistance in series or rheostat to adjust the field current. And we have separate supply. So we're talking about DC separately excited DC machine. And the voltage here will be VF. And we said if you want to make shunt DC motor, just connect the field winding in parallel with the armature, so it will be supplied by the same source. So that's a simple one. And then of course you have mechanical load on the shaft here. You got load connected to the motor where you put the load. And the current here would be IF. And the objective of the field winding to produce flux, magnetic flux. And so the magnetic flux will be directed to the armature. So you have the flux from the field, and you have the voltage that will allow the armature current to flow through the armature. So you have the interaction between IA and phi, then it will start to rotate. So what is the relationship between the torque? You have here the torque, it will be rotate in a special or a specific value of the speed, omega m, and you have also torque supplied to the load. So what is the relationship between the speed and the torque? We'll start with the equation of the voltage. We say that the voltage, the terminal voltage, will be applied to the armature part, so it will be distributed. Some drop will be across the resistance, will be RA, IA, plus EA, the back EMF. And we have two relationships. They are so important. Two equations. Do you remember what there are two equations of the DC motor? That you should always remember these two equations. Exactly. EA, the relationship between the speed and the back EMF. And the second one, T, yeah, the relationship between the torque and the current. These are the two basic equations between us. So I'll just write it down. EA is equal constant. That's the machine constant. We can call it KA. Times phi times omega. All right, omega. And the second equation is the torque is equal to the same constant, phi IA. And we said that KA, the machine constant, in both the torque equation and the EMF equation, both numerically are equal. Maybe they have different units, but they're equal numerically. If this is equal 9, this is equal 9. Now I want to find the speed. we find the speed from the back EMF. Of course, this is the equation that will help us to find the speed. So let's find the speed. Omega m will be equal to the armature voltage back EMF divided by Ka phi. All right. What's EA? How can you find EA? Which equation you can find EA? The first one, right? So I will say I have here Ka phi, and I have so EA, which is equal to the voltage Vt minus the drop RAIA. So let's separate them into two separate terms. So I have Vt divided by Ka phi minus Ra divided by Ka phi times I. Now I have equation. It tells me the relationship between the speed and the current. That's good. That's good. But I'd like to know the relation between the speed and the torque. The load would be the torque and the speed. So I have a relationship between the current IA and the torque. Where is this equation? Is the second equation. So what's IA from this equation? IA, you can say it's equal torque divided by Ka phi. So let's replace it. So omega m will be equal the terminal voltage divided by Ka phi minus Ra, Ka phi, and Ia is equal torque divided by Ka phi. Let's collect the constant terms together. So I will write omega m equal Vt over Ka phi minus Ra divided by Ka phi squared, because both are the same, times T. If we are operating the DC motor under constant terminal voltage, it means the supply Vt, this one, constant, I'm not changing. If it's 120 volts, 120 volts. So Vt is constant, K is constant, phi is constant, I'm not changing any field. So this term will be constant. I will call it omega naught, constant term, where omega naught is equal to Vt over Ka phi. And Ra over Ka phi squared, that's another constant. Let me call it just K. K will be equal Ra divided by Ka phi squared. So the equation now can be written in a simple way. Look at the equation here. That's the equation. And just any constant term, I will just keep it constant, call it one term. So omega m is equal omega naught, because I call this term omega naught. So I'll say omega m equal omega naught minus all this constant called K T. That's a nice simple equation, straight line equation. So the relationship between the speed and the torque is straight line. Let us sketch it together. We have the x-axis torque or armature current, because the relationship between them is just constant, right? T is equal Ka phi K times Ia. So both are the same. And the x-axis, that will be the speed, omega m. What happens when T equals 0? When the torque is 0, means you don't load the motor on the shaft. Shaft is just running free. What happens if T equals 0? What's omega m equal? Omega naught. So it'll be here, omega naught. That's why I call this constant omega naught. No load speed. That's the speed of DC motor when there is no load. And then the straight line will have a slope equal to what? What is the slope of the straight line? Okay, and negative, right? So the straight line will be like that, negative. So I can sketch straight line negative. Till it comes here. I'm exaggerating actually. The slope is not that steep, but just I want to do that for something. At this point, what is the speed of the motor? 0, that's right. We call this T stall. the stalled torque, the torque that make the machine plugged, not rotating. And that's very dangerous because it will draw high value of armature current that can burn the motor if it's not protected. We never do that. So actually, the slope, I'm exaggerating because the slope is really, if you calculate the slope k is equal RA, which is very small, like 0.2, 0.3, 0.4, divided by big number, so you get it, the slope. Let me tell you what exactly the real slope in real life would be similar. That's the speed axis, and that's the torque. So if we sketch the real one, omega m torque or armature current, and that's the no load speed, it will be like that. Small drop, almost constant DC mode. That's why we use the application. If we need constant speed with just small control, DC mode, the speed is almost constant. That is a drop. 5%, something, if you load it, 5%, nothing more. I'm exaggerating here for something, because sometimes we do the tests. But when we make the test to measure the stalled torque, we don't apply the nominal value of the voltage. Like if the motor went 20 volts, maybe you apply only 20 volts. Why? Because if you want to make this test, the speed, I mean, you give power to the machine and then you lock the rotor, is not rotating. So what happened to the current? Increasing that. So they make small amount of voltage apply to the terminal of the DC motor to be sure that the armature current will not exceed that. Why do you do that? For testing DC motor. Because I mean, there are testing, you can use this value, so you can measure the constant of the machine, the armature resistance. Maybe somebody will say it's easy to measure the resistance of the armature by putting voltmeter just across. No. The DC motor, every time rotating the angle change, the resistance change. Okay. So that's the characteristic of the speed, torque, and the equation that we just explained, omega m equal omega naught minus k t. And the slope is very small as well. And of course, if you want to calculate the omega naught, the no load speed, it's very easy. We got here the equation. You got to know what the value of the terminal voltage applied to the terminal of the DC motor, BT. You got to know the machine constant, and it's easy because we explained that how to find the machine constant. K is equal P times Z over A to pi. So you got to know the number of poles, the number of conductors, and all the given. So you can get Ka. Phi, that's the magnetic flux, and you can find it from something called magnetizing curve. This will show you the relationship between IF and the voltage produced or the phi, we call it magnetizing curve. You can get it. So you can calculate the no load speed. Or another way, you run the machine, you don't load it, and just measure the speed using the dynamometer that we do it in the lab. So that's the relationship between the speed and the torque. Since now we know the relationship between the speed and the torque, now let's just go, how can we control the speed of the machine? There are three methods. So speed control of DC machine. The first method, it's called armature voltage control. The second method, by controlling the field, called field control. In armature voltage control, we change the terminal voltage. In field control, we change the flux by changing IF. The third one, armature resistance control. by changing the value in the resistor. That's an armature. Let's take one by one. The first one, armature voltage control. How this will control the speed or change the speed of the DC motor. So the first method is armature voltage control. And do you have any question? Just you can stop me any time. Okay. We'll go back to the same basic equation that we drew before. What is the equation here? Yeah, I'll go back and take this equation, we just did. Because I mean, all method of control will depend on this equation. And I'll put it there. Last time we said we were studying the characteristic of DC motor, the change of the speed of torque. So we said we are going to fix the terminal voltage. Now I want to control the speed. I want to change it. So I'm going to change the terminal voltage VT. So now I can write the equation this way. Omega M equal, I have Ka and Phi, I'll keep it constant. I'm not going to change anything in the field. So I have 1 over Ka Phi times Vt minus, this is another constant, Ra over Ka Phi square and T. So I will write the equation omega M I'll write the equation omega M equal to, I call this constant, let's call it K1 Vt and call this K2 T. I have another straight line where K1 is equal to 1 over Ka Phi and K2 equal Ra divided by Ka Phi squared. So that's an equation of a straight line. Let's sketch the relationship between omega and voltage, how the speed it changes with voltage. So I will have, this is, I mean, y-axis the speed, and that's the terminal voltage, and that's the speed. So when the torque, let's say, I will say first, what about if the motor is not loaded? The torque is equal 0. If the torque is equal 0, so I have the, if torque equals 0 in this equation, so the omega M equal K1 Vt. So it will be just a straight line from the origin. So this straight line shows how the speed of the DC motor is changing when the motor is not loaded. That's when the torque is equal 0. So obviously the relationship is linear. The speed is increasing linearly with the voltage. Every time you increase the voltage, you increase the speed. That makes sense. What about if you have torque? Any amount of torque. So this equation, if you want to just remember how you sketch it, call Ym like Y, and Vt the one that independent variable, call it X. So that will be Mx, and this one will be like the y-intercept. So what does it mean? It means that will be the same slope that we did with the torque equal 0, but it will not start from 0. It will start from minus C. So if you make this one here like that, and then you can, and if you sketch straight line parallel to it, and just you extend it, that's not exactly parallel. So this is the characteristic when the torque has certain value. The same slope, but the only difference that you will feel, you can start from voltage equals 0. You got to start from certain value, positive value. Why? Because I mean, when the speed that's here at this point, the voltage has value, but the speed is equal 0. It's very obvious, when you have any motor, and you put the load in the motor, and then you try to start it. It's not rotating, but it's trying to build up the energy, enough energy to start. So that's why from 0 voltage, it will not rotate. It has to overcome the all, you can say the all opposing forces, opposing torque against the load. But it is the same thing. Then after that, you're increasing the voltage, the speed is increasing. And obviously, if you want to make more study, if you at certain voltage here, if you go at certain voltage here, if you are not loading the motor, you get speed higher than when the motor is loaded, which makes sense. If you have a blender and then it doesn't have anything, the speed is high. If you load it, the speed will get low. So makes sense. All right. So that's the way that to change the speed of the motor with changing the voltage. Let's now go to the second method. How I can control the speed? By changing the field and keeping the voltage terminal constant. Call it field control. So let's say that you have the DC motor here. You have the armature resistance, and you have the terminal voltage. You will keep it constant this time. And let's assume that you are connecting the field in parallel to the armature. That's your RF. So the current here, the terminal current, will be divided into 2 currents, armature current and field current. And the field current will supply the field winding, the armature, energizing the armature. And let's now look for the field. Again, we have the same equation that we're going to use the same equation. This is the same one that shows the relationship between the speed and the voltage, and would change the parameter. That's, I mean, the old trick. You put the equation, see what you want to change the speed. So now the voltage is constant. I'm keeping the voltage constant here, and the resistance, of course, constant. But phi, I'm going to change phi. All right. Okay. So first, I have to know what is the relationship, or what the variable that produce phi. What produce phi? What is the variable in DC motor responsible for producing flux? IF. That's right. So IF will pass in the winding and then make the flux. That will go with the armature. So you can say that phi is equal constant time IF. So if you remember the constant Ka phi, I'd like just to call it one name. Ka phi, it will be constant Ka, and phi is equal another constant times IF. So I just can call all this one Kf. So Ka phi is equal Kf IF. Now, okay, I make a proportion to the field current. I will go to the main equation and I replace Ka phi by Kf IF related to the field current. So you have the speed equal to V term divided by Kf IF minus Ra Kf IF, but both are square, torque. All right. So that's the equation that we have. let's say for a particular condition that no load, when you don't have load, and let's say when the torque is equal 0, what is happening? We're going to do the same analysis as we did with armature control. If the torque is equal 0, the speed omega m will be equal to Vt over Kf 1 over If. I'm focusing on the field current now. What happened if I change? So that will be the equation. You can call it another constant if you wish. If the terminal voltage is constant, so just call it all K over If. So omega m is proportional inversely with the field current. What does it mean? It means every time the field current decreasing, the omega is increasing. I can sketch it like that. But I'm not going to sketch it from 0 to 0 for the whole range. I'm going to choose special range that will be like something like that. And actually it's not straight line. It's proportion, yeah, but I cannot say straight line. Why? Because the relationship between the field current and the flux not linear. If you remember when I sketched for you the magnetizing curve, the relationship between IF and pi or EA, it's look like that. So it's not straight line. It can be straight line in specific reason. You can, if you like, you can take a small piece of the curve and then you approximate it by straight line and you make the relationship straight line. That's okay. Over small range, you can do that. But what to understand that the speed is proportional inversely with the field current. Okay. If you have, if you look at this equation that we did, and let's just write it for a specific value, how it change with torque. If you say, okay, I'm going to adjust it to some value of the field current IF, and I'll fix at this one, like what you're doing in the lab, you say IF is going to be equal 0.3 amp. So how the thing will it change? Well, it will be the same curve we did in the armature control. Now you want the relationship between the torque and the speed, and we know the I'm going to use the equation now. That's you can say constant, some kind of constant minus call it K3 and K4 sin t. I'm writing this equation again. I'm considering this part constant, terminal constant, and I fix IF at certain value, so that be constant. So constant minus constant t. So I will get the same here. If you say that's omega naught, to be like that. That's when you fix it at certain value. The question now, all right, I'm going to change I field at another value and see what happens. So what do you think will happen? Let's say, for example, IF1, it was 0.2 amp. And now, what happens if you increase IF to 0.4 amp? What happens? Like, yeah, the speed is going down. So what the characteristic will look like? To let's say that IF2 is bigger than IF1. So the speed will go down. That's right. So what the characteristic look like? Yeah, it will be the same line, right? But check parallel. So you start not if you say this is omega naught 1, no load speed at IF1. So you'll have another one, no load speed, lower, but you'll do the same straight line, parallel, the same slope. That's IF2. So every time you are increasing the field current, the speed is decreasing, but taking the same characteristic as a change with the torque. That's the field control. So that's how you do the field control. Okay. I'd like to talk about something about field control a little bit, because there is practical, they use it actually in real life. when we control load, usually do that. We start control from 0 till it reaches the nominal speed. Usually by armature voltage control. So if you have the machine, you want to reach the nominal speed. Let's say the nominal speed is 1200 RPM, like what we have in the lab. So how will we control that? Say, okay, and you have load. Okay, so you will start increasing the voltage gradually from 0 up, let's say 120 volts was the rated value, till we reach the 1200 RPM. After that, you do not change the terminal voltage. Use different kind of control. That's what I want to talk about. So when you have start from 0 speed, when the speed 0, you want to go to the nominal value. That's mean nominal. Nominal value, it's written, you know, on the plate of the Numerical. So how you use, what type of control you are going to use to change VT. VT will start from 0 till you go, obviously, to the nominal value too, usually, very close to it. Then, speed control beyond the nominal value of the speed is obtained by decreasing the field current. After that, you start to use the second method. And we call it field weakening, because you make it weak. That's strange. You make the field weak. The speed you have. Does it make sense to you? You make the field weak, you get high. Why? 1 point bonus. So answer this question.
Does the field current, does it kind of work like a brake at some point against the motor? Like it stops the motor from sending it back to the can because the flux is like
No, I know. Actually, the opposite. When the field current decrease, the speed increase.
Right. But like the field current is flux which controls the motor.
It reduces the flux, that's right.
So if the field current is lower, will the flux be lower?
The flux will be low. That's right. Why? Because of what?
Speed.
The formula.
Yeah.
So I want to give the explanation. I mean, you can just say the cause of the equation. You can look at the equation, see the effect, and you tell me what's happening.
Right.
Yeah.
But it's that simple. It's just, since they're inverse, that's what's happening.
Why?
Yes. You're saying as the magnetic field gets weaker, it is faster, right?
Yeah.
And you said that the flux goes down. So if it just has like the amount of resistance that is acting on the object is just from the magnetic forces, like I guess like having.
Oh, why? Do you mean that when the flux gets less, so the resistance of something that it will be decreasing?
Well, I mean,
so
the magnetic field acts on what is rotating around.
Yeah, but if there is no kind of resistance, I understand what you're saying, but it's not kind of resistance. Flux, yes.
What if it's because when the field current goes down, it allows the armature current to go up?
Why?
Because they are in parallel. So if the field current is high, the armature current will have to be low. So lower field current means greater armature current, which means it can spin faster.
It should come get high. This is true. The measure current get high. Yeah. The measure current get high. That's right. But that will cause the speed to get higher.
Yes.
Why?
Because there's more speed. There's more current going through the armature, so there would be greater internal flux, which would spin it.
The flux really is weak.
Gives you a higher torque.
Yeah, you can have higher torque. That's right. But okay.
Do you have less flux hitting the field like like a plate, I guess? You remember on the magnetic circuits when we had an air gap and we moved the thing over that was in the middle of the air gap, we moved it over. The flux didn't have as much room to go through, so that would decrease the flux, which means it wouldn't be as much on the other side. Speed to go up. I don't know. Made sense when I was
Yeah, I mean, maybe. I mean, you said about the air gap, right?
Right.
The flux is weakening, so you're saying that not.
I don't know where I was going with it. It made more sense in my head.
Okay. First of all, the weakening of the field or the flux happened by decreasing the field current. So IF will decrease. And that's why they call it field weakening. That's very important. When this happens, call it field weakening. We'll take it step by step. What's happened at the base state? What happened to the armature terminal voltage if it stay at its rated value? If the armature current is not to exceed its rated value, that's very important because they said something very important, that the armature current will be increasing. So we have to keep the eye on the armature current not to exceed the rated value. That's right, will happen. Armature current will increase. If the armature current is not to exceed the rated value, because we want to keep the heating limit as it is, the speed control beyond the speed is restricted to constant power. We call it constant power. It's like, I mean, you cannot get more than the constant power of the machine. And the power at this time will be equal to VTIA, and we want to keep it constant. Let's approximate like EIA if we ignore the armature drop, because R is a small 0.1.2 ohm. In this case, the torque will be equal to the power divided by the speed. And we want to keep this constant. How will keep it constant? We'll keep the eye on the current armature not to exceed the limit while the EH changing. So when the flux weakening, the EA drop, and then the all voltage will be applied to the machine. After that, then we'll give it power to speed more. But at the same time, the current of the armature will be increasing. So that's why we have to keep the eye on it, not to weakening a lot. Because when the field, the flux drop, EA drop, the all voltage now apply to the machine again. And if you ignore the drop, the voltage is increasing. So the speed will be increasing. Because we said that in the beginning, the armature voltage will increase, but I didn't increase the voltage. It's constant. But what happened that the drop in the E, so the current is going more, so it's replacing that decrease. So it to make it getting powerful and getting speed again. But the only thing that we cannot weaken the field for too long, because or for too much value, because the current of the armature will be increasing rapidly, and we have to watch it, and then we stop weakening the IF. So that's, I mean, how you do the. So actually, the field the weakening field that we did is a field control. It's like what we explain here, and we know from that. And as you answered the question, when the field current increase, the speed will drop, right? So the opposite, when the field current decrease, so the speed will go up. And that's what we call it field weakening. And this one applied after you reach the nominal speed. The last one, it's easy one, and it's a classical method. And it's replaced now by using power electronics, but the concept of power electronics depends on this one, using armature resistance control. What's happening in this one? You have the motor here, and you got the resistance. You don't have control over it, but you are going to add resistance intentionally. You will add resistance here, and that's your supply. Let's say shunt. So that's the voltage of the supply terminal voltage, and that's the current IT, and that's the current IA. And then you have a variable resistance here. Call it R restat or R whatever, RS. and then you got the field. That's RF. And the current here will go IF. So I will use the same equation that we did. Obviously, I'm going to change the resistance. And what happens when you change the value of the resistance? Let me write the equation so you can see it. Vt is equal, I will get back to the final equation, we don't have time. So Vt over K phi, we proved that already, minus Ra over Ka phi square times T. That's the equation that we use for explaining the relationship between the speed and the torque. Now, what happens if you change the resistance? If you add resistance to the armature, are you changing the resistance? What's happening? What's happening to the total resistance? Let's take step by step. When you add resistance to the armature, so what's happening to the total RA? Increase. The total RA increase. And if you look at the equation here, the Vt is equal EA plus RAIA. So if you increase the resistance, so the drop across the all resistance increase. And you are fixing the voltage supply. So what happened to the EA? Because in this case, this is your EA. EA is always, or the back EMF is always equal to the voltage of the supply, Vt, minus the drop, RAIA. EA, the equation of EA, is equal to the voltage of the supply minus the drop. Now I call it Rs plus Ra times Ia. So if Ra only there, you don't have any series resistance, so you will get the nominal value of E and the nominal value of speed. But if you are adding resistance in series with Ra, so the total resistance of the armature circuit will increase. So the drop will increase. So E will decrease and the speed will decrease. So that's the way that you control the speed. And they use this method, this classic method, they use it before to start the motor. Because as we said before in one example, that when you start any motor, and DC one of them, the starting current usually 5 times the nominal current. Like if the nominal current is 4 amp, the starting current will be 20 amp. So to avoid that, they put resistance in series. And it's like, they started the resistance from the high value and started decreasing the resistance a little bit. So it will build up and the speed will be growing, gradually. So that's the way that you are used before. And they still use it in small motor, but power electronics replace that. They are using some technique called pulse width modulation by controlling the voltage. You have the battery there, 12 volts or 120 volts, whatever fixed, but there's a converter. If this is the battery here, positive and negative, and then this is the motor that you have, then that's the negative, and then the positive here we have something called chopper or a switching regulator. This chopper is like electronic. It turns on and off quickly. So if you have 12 voltage, and if you interrupt it, you make on, off, on, off, on, off. So let's say that it's on here, off, on. So the average voltage will be lower. And they call it pulse width modulation. So this pulse of on, you can decrease, increase. For example, if you make it bigger and the off smaller, so that's on. So the average voltage will be higher. So by changing the width of the pulse, and that's electronically be done. I work even with that one, design it. Easy, simple to do it. And the advantage of this one over the resistor that you insert in the armature, that the other one has power loss, cover loss, I square R. But that's the method used before. They still, of course, use it till now, but with a small model. They are not going to bring, chopper and the cost themselves. And originally, the current is very small, doesn't exceed 1 amp, for example. But if you talk about DC machine, big one in factories or anything, it takes like about 20 amp. So they use, the power electronics. question? Let's solve one example and we'll be done. A variable speed drive system use DC motor that's supply from a variable voltage source. And they want to control it in this way. That's mega. And they said, I mean, do you want to have like the torque fixed, and after that work in other region, which will be like constant power. If I sketch the other here, it means here the power is increasing because I'm changing the voltage. I'm using here the armature control by increasing the voltage in this area. So the power will be increasing. I'm increasing the voltage to increase. And then in this area will be constant power. So the torque will be like. So the drive speed is varied from 0. I want to start from 0 up to the nominal speed, which is equal to 1500 RPM. By changing the voltage. And the voltage, the supply, it's available like 500 volts. So I can change from 0 to 500 volts. And when I'm doing that, IF will be constant. So that's region 1. That's what you do. So we want to determine the motor armature current. In this case, what's the armature current? So to make the torque constant, as you see, the torque is constant with the speed. You want to keep the torque constant. It can supply constant torque. You want to keep the torque constant at 300 Newton meter up to the speed. So you want the speed increase, but you keep supplying constant torque. So in this case, what's the value of the armature current? I'm talking about only the first region where the torque is constant. So we know that the speed I want to reach 1500. And I know the terminal voltage from 0 up to 500. So when I reach this one, I will reach the nominal value. I will get 500 volts. You reach the nominal value when you reach the nominal value of the voltage. And of course, I mean, to find the, we know that E in general, E is equal to Ka phi omega. All right. And if you don't have omega, you can replace it by n. So you say Ka phi time omega is equal pi n over 30. Okay. So from this equation, if you know the voltage E, the back EMF, you can, and you know the speed, you can get the all constant Ka phi. But the problem is, I know n is 1500. That's the speed I want to operate at, but I don't know the armature voltage. EA, but I know the voltage terminal 500. But the problem, they don't give you RA. Well, in this case, RA is small, especially big motor also, because big motor they make it from thick wire, the rest is almost ignore 0.1 ohm. So if you ignore the drop and you want to make fast calculation, you can say that the EA is equal VT, right? Because you know that VT is equal EA plus RAIA. So if this is small, you ignore it. So you can say EA almost equal VT. And that's good, because if you do real life, it's equal 490. So it's not really effective. So I would say, okay, EA, it's almost equal to the voltage term, which is 500 volts. When I reach the 1500 RPM. If you got that, so you got EA and you got the speed nominal 1500, you can get the value Ka phi. This is the only constant that you. Why I'm getting this Ka phi? Because I want to calculate the torque. Why I'm going to calculate the torque? The torque is given. That's how I get the current. Why? The question is find IA to support this torque. And I know torque is equal Ka phi IA. I know the torque. I want to get IA. I got to get Ka phi, the constant. So how I get Ka phi? I get from the other side, from the other equation, the speed and the voltage. And I have it here. EA is equal to Ka phi omega. So I can get from here. I have omega. I don't have EA. That's the technique. Okay, but they give me the armature resistance. It means ignore. Okay, so make EA equal VT, get KFI, put it in the equation, put the torque, because you want the torque to be constant at 300 Newton meter. And this already, we got it from the voltage, then you can get IA. You get the armature current that will support this torque. So when you do some calculation as an engineer, sometimes you make approximation, especially with big machine. Usually EA, if RA is not mentioned in the problem, it means it's very small, can be neglected. So you make the EA is equal VT. And by this way, you can get the constant that you can use it to find the armature of the current. Okay, so that's, I mean, the next time I will put the second part. When you operate at constant power, you use the weakening, the field. Any question? No.